should be very much of interest for this audience. This is quite prestigious conference about power systems. It's by every 2 or every 3 years?
Every second year.
It's every 2 years.
Every 2 years. So the next one will take place in Durham, beautiful place in north of England. So if you come, you'll have a dinner in a medieval castle. It's planned, and here are the dates. It's July next year. President is general chair, and I'll be the technical chair, which means if you send any papers, I'll have a look at them. Here's the website, www.dur.ac.uk/pmaps.2014. So if you have any questions, please ask Chris or myself, rather Chris, because he knows far more about it than me.
And I suggest you, if you look at your laptop, Google images of Durham, and you'll see the beautiful castle and it's a beautiful place. So I'm supposed to announce that the video, the camera's on. So if anybody objects to us this being taped, let me know. I'm supposed to take responsibility for the fact that this is being taped. I don't know why I'm responsible. So if you're going to sue anybody, it has to be me, I'm told. But does anybody want to start with a question for discussion? Maybe somebody who's been quiet for a while. Yeah.
I think start with a question, particularly if it's a bit dumb and then nobody else minds. Well, really, I guess primarily relates to Janish's talk, but what are the benefits of greater integration within Europe? I mean, Janish talked about Ireland being small, and this obviously causes problems. Britain somewhere in between. But is there a drive for more connectivity? Is it worth it? Is it worth building more interconnectors because of the much greater uncertainty in the future? It's not obvious.
Yeah, well, so that was actually part of my presentation, but it was Sean gave me a sign that 2 minutes left, so I didn't speak about it. Of course, the main power systems are big and interconnected in Europe. I mean, Britain is not connected due to geographical reasons, but the whole European network is interconnected. The United States are divided in 3 interconnections. So there's a trend, the bigger the size of the system, so the main driver is sharing frequency reserve, which is something what I've been talking about. Because if there is a loss of a large power station, then you have to cover for it. In this country, its size will be 1,300 megawatts, which means you have to keep 1,300 megawatts, actually a little bit more than that, in reserve in case something happens. If you connect 2 power systems, you can calculate probability that you actually is far less than that. That means if you connected Britain to Europe using either AC links or equipping AC links, existing DC links, with controllers which would imitate AC connection, it means it would draw in more power if frequency is dropping, then basically you would be able to share reserve with Europe. It means you wouldn't have to keep 1,300 megawatts, and it's going to be 1,800 in future when the big nukes are being connected, but it will be far less than that, about 1/3. So it will be huge savings. And then that's the main reason the European power system is interconnected, to share reserve. Of course, there's a positive side. The negative side is with any interconnection is stability problems. Because if one part goes down, it can bring the whole system down. And there was an incident in 2006 when in Germany they opened some transmission line to let the ship pass through the river, and the disturbance, they mishandled everything, and disturbance spread through the whole Europe, and millions of customers were disconnected even in Spain, which is far away from Germany. So of course there are benefits and also dangers. The general view is what's the optimal size of the power system, which is, I think, is more or less your question. So does it make sense, for example, to connect the island? For example, at the moment there are attempts to connect the studies to connect European power system to Russia, and that's a huge system. So of course you would have some benefits in cost of trading, you would have benefits in terms of sharing reserve, but technical problems in running the system as a one integrated system, I think, would be excessive. And I remember unpolished. And I remember until the Berlin Wall fell down, Poland was connected to the Soviet Union. So there was basically a system which was spreading from Poland up beyond Ural Mountains. And they had huge technical problems to keep stability. This is what I was talking about, the dynamic stability of the system. So they were restricting power flows in order to keep system together. So you have basically vectors pulling in two different directions. Of course, it makes sense to make it bigger. There are huge economies of scale to be had. But on the other hand, you make system more vulnerable to disturbances. And there's optimal size. And the consensus at the moment is more or less Europe or Eastern or Western interconnections are the maximum sizes. So I do not believe that actually Europe will go to connect Russia to the system, because it would be too big and it would create too many problems, technical problems. European view.
First, Shaji.
So an economical question related to that. Assume we connect the UK with the pseudo AC link to Europe, the way you said. This adds value to the UK grid. Probably doesn't add any to Europe. Europe, which doesn't exist. At the end, you connect to the Netherlands or to France, right? To a given country. So what would be the money flow? What would be the value? Would you pay to the French network to be connected there?
Well,
and how much, and how do you
Britain would
this,
save
on
running this frequency reserve, reducing it from 1,300 to, I don't know, 500, let's say. It will be huge economies, huge savings, and that could help persuade the French and the Dutch in order to connect them.
But then the French and the Dutch push a bit of that to the German.
The Germans wouldn't like that.
That's the political, of course, haggling. Which
It's an economical thing. I mean,
yeah, of course, there's
this
economic
is not
side to
sorted
it.
out, or?
Well, I mean, the national grid is undertaking, as I understand, studies to basically address those problems, because of course they know about it. They're looking at Ireland, so there are conceptual studies and they're thinking about it. Of course, there's a political thing in this country. Connecting to Europe is right. So there was a UKIP, UK Independence Party, which is against stronger links with Europe. So there's a connection between politics and technical thing. For example, I mentioned this 2006 a near blackout in Europe, and Britain was not affected by it at all because there was a DC connection. And even to the extent that although France was then in deficit, so basically it would make sense, but at the same time France was exporting power to Britain according to contracts, which is an nonsense, because the first thing they should have done is to cut off the connection to help to maintain the power balance. But they didn't do it. I mean, I never got the answer why they didn't do it. But basically, that shows you that
there probably was a contract where
it's a contract, so maybe
non-delivery-
penalties would be too big.
Exactly.
But they were risking blocking the whole France, you know, with millions of customers and
I think there was
astronomical losses.
3,000 megawatts of wind in Spain that was disconnected just because the frequency started to fall just at the time when that wind was required.
That's another thing. Yeah.
So you've got various sources of renewable energy which, had their protection systems not operated, they would have supported Spain and that whole Iberian Peninsula and kept the lights on. But because the protection systems had been set that when the frequency got to this particular level, which was almost unheard of on the really firm European network, they got disconnected and exacerbated the whole problem. So it did become very much a cascade scenario. But equally in the UK, we had an incident where Sizewell B tripped off, and then a few minutes later, another power station up in Scotland, totally unrelated, also tripped off at the same time. Caused a lot of protection systems in this country to operate, and clearly we didn't end up in a black start situation, but had it lasted many minutes longer, there was certainly a possibility of that. So where in Europe the frequency stays at about 50 hertz and it doesn't move from that very much at all, the UK being, or Great Britain being a smaller island, we have still 50 hertz, but on average over a day you can have things between say 49.9 and 50.1, and that's all quite acceptable. You go over to Ireland, being a smaller island, you have frequency variations of 49 to 51 hertz, and that's quite acceptable. You go to Shetland, again, part of the GB market, and you've got a 60 megawatt diesel power station, and the frequencies, well, dare I say, all over the place. But it's as size gets smaller, so does this frequency variation, and you need to have defensive mechanisms in place such that you can try and recover from, as Jonas had on his slide, that initial dip. You want to try and cut it off as quickly as possible. Now, I mentioned our storage project, and with storage, just like with any other DC source, if you've got a control system that can respond to that requirement to provide the primary frequency response, instead of a generator which has the governor, which will give a response within 2, 3, 5 seconds, the power electronics of a storage device can be providing that within a few milliseconds. So yes, a 6 megawatt storage device is going to be neither here nor there, but if the business case can be made that there are services that are of value to the likes of National Grid and suppliers and the network operator, instead of just having one 6 megawatt device, you could have 100. And then that becomes sizable size. It becomes part of the solution in that it does provide the frequency response, and there are going to be, probabilistically, you're going to have storage devices in the right state at that right instant in time, which are going to be able to offer the service. So there is an awful lot about trying to keep this balance that we take for granted.
With comment here.
I think what Janis just said was the reason for integration before the internal market, and at the time it was UCPTE that managed to have that integration by sharing the reserve. But the real movement, the real incentive for the integration was the internal market, which gives a completely different idea. The idea of the internal market was to enlarge the size of the market so as to introduce competition in the system. And so the idea was to be able indeed to allow for bilateral contracts between different agents in a much broader market. And that integration has so far not really been done, in the sense that those long-term bilateral markets are so far not possible. So it was not only to share the reserve. Sharing the reserve, that was something that was done before already, either through UCPT or through just bilateral contracts between two neighboring countries. And that computation that in fact they could gain by sharing the reserve was well understood before the big movement of 1992. But that is still in process. In fact, the discussion for fully integrating started in 1998 with the Florence Forum. And on that, we made some progress, but not much, and definitely not to the extent that we would have an integrated market.
Okay, so another topic. Actually, I guess there's a pause, so I'll try it. This issue of information. So it's just music to my ears to hear. You have I don't know how many millions of transformers and cables and all of this, and of course you don't want to have a signal sent out from each one. You don't want to measure. But is there any hope for some sort of a data mining? I mean, sort of classification scheme, so you can basically take 0.5% of the resources and sort of categorize them and sort of try to learn when you should service this class of device. So basically the classification might be how old it is, what technology, and what kind of weather it's seen over the last.
Exactly, and certainly things like age and manufacture are things that are never going to change. But one of the variables is how hard has it been used?
Yeah.
Because a transformer that's been run at 100% of its rating is probably been designed to last 40 years. But a lot of the time we don't utilize our assets much more than 50%, especially where we've got two circuits running in parallel. We would have two overhead lines, two transformers, two circuit breakers, and then it radiates out to a radial network where the utilization does increase, and there you have variations between perhaps a 20% utilization to perhaps 120% utilization.
And so that's a feature you'd want to, can you estimate those features? I mean, without directly measuring?
Well, that is perhaps one of the opportunities we may be faced with the smart metering and the data that comes along. Over the country, there's going to be something like 40 million smart meters connected to the customers in Great Britain, and our own network has about 8 million customers, and we already know the meter which is connected to the transformer, and you could start thinking about, well, can you add it together and aggregate the data so that you can work out, well, how hard has that transformer been utilized without having to put some monitoring in at the substation to effectively confirm what could be calculated. I think what we're at the stage at the moment where traditionally we have built a conservative network which has got capacity in it, and that has allowed us to not really actively manage our low voltage networks. And we're now into a situation where we know the loads on where it leaves the primary substation, where the power, effectively the last point of, I call it real-time monitoring, but it's the control engineer knows the state of the circuit breakers and knows the current that's flowing through those circuit breakers. But there on afterwards, we have various models which try and represent what's happening, and the data we've got is very sparse, and as I indicated, we have these maximum demand indicators which are they don't really tell you exactly what the network was doing at the time that maximum demand occurred. So there is a tolerance of perhaps 50% error maybe in some of the readings, but that is not I think we have the opportunity to use the smart meter data come 2019 when they're all installed, so we hope that we'll be able to make use of this data and try and understand, well, what is the utilization of the low voltage cables, what's the utilization of the transformers, where other low carbon technologies which are potentially could be quite disruptive in changing the shape of the demand curve, where do we need to make our next investment, and what is the appropriate investment? Is it a case of building another distribution substation, or is it putting in some larger cables because that's all that's required? So I think we do have a large amount of data coming in, but it's nothing compared to potentially the half-hourly readings from 8 million customers, and trying to aggregate it together and say, well, what do you store?
That's the thing. You need
It's trying to say, well, here is a demand profile. This customer looks like a profile A, but with a scaling factor. So we'll store his data not as the half-hourly data, but as a demand profile curve or a combination of curves, and say, well, this represents that customer.
Yes, I mean, you can imagine the kind of features you want is their peak usage and their variability of usage and sort of ramp.
Yes, and things like demand response are going to become a fact of life, and it's trying to understand, well, what customers are prepared to respond to demand response signals. You know, if you've got a customer who's got the capability to offer, for example, if you have a factory, he can perhaps say, well, I'm prepared to reduce my demand by a megawatt. That has value when you've got an overloaded network.
And just to follow up on that, so I mean, given the fact that that has value, the idea that somebody can inject power to the grid and completely anonymously, it sounds, I don't know, it sounds like just, you know, putting on a mask and doing your laundry in the middle of the road. I mean, it just seems so outrageous that, you know, somebody can just, you know, do this damage to the grid
Well,
completely anonymously. It just doesn't make any sense. I mean, to get a permit to inject power to the grid, you should be, you know, it has to be transparency of what you're doing, and there should be rules of the road. I mean, you should.
There are the rules applying down to a certain level. No, for example, we have this with photovoltaics. If they're up to 16 amps per phase, this idea of a G83.
16 amps per phase.
16. That is about just short of 4 kilowatts.
Okay.
The installer is obliged to tell us that he's done it within 30 days of the installation.
Yeah.
So no checks have been done, and generally you ask yourself, well, 16 amps per phase isn't compared to the size of the profile of an individual's demand. It very quickly disappears out.
Yeah.
The problem occurs when you have a cluster where you have, say, a housing association, and each house down a street has now all been, each roof has now been covered with photovoltaics. You suddenly have large generation during the day when everybody's at work, and then nothing at all in the evening time when you really do need the energy.
Wow,
So yeah, smart grids have got some challenges, and
but somebody, I forgot who it was, somebody mentioned 13 gigawatts of, I don't know if that's gigawatt hours or gigawatts over a year, I don't know, but unaccounted for generation.
National Grid.
What's
That
that?
was National Grid that
National
mentioned
Grid.
13
gigawatt hours? Or, I mean,
No, I have 13. I mean, that just seems an incredible figure.
I wanted to clarify what exactly that meant. Who was that again? But there's a
Maybe
huge
it was
amount of power.
Maybe it was gigawatt hours per year.
yeah, it sounds like
Yeah, in which case that
Energy.
makes sense.
The thing where they didn't have meters. That
No, I
was
can believe that being gigawatts when you wrap up things like CHP below the threshold that's got to be nominated to grid.
2 gigawatts of solar,
Yeah.
2 gigawatts of wind, and then
I think.
But
What do they mean by not knowing? Because
Yeah.
we're able to tell them no, because as I say, we have a telephone directory of where we've got generation connected, but what we don't know is how much they're generating at any particular instant in time. So we know that there's a 50 kilowatt CHP plant outside, but we don't know whether it's generating or there's been multiple ones installed because it was such a good idea, and we're unable to. We don't have any real-time monitoring of that because it's by the time you put in the monitoring equipment, potentially it would kill that project off completely. So it's almost a case of, rightly or wrongly, we treat it as negative demand. So what I was my slide with the demand curve on it, just even in the Cambridge area, there's 8 megawatts of generation somewhere around, but as to what impact it has on the demand curve, we really don't have any visibility of at all.
Yeah, just as a quick aside with that, there's a split between renewables and like solar and wind and other types of generation at distribution level, because you can reconstruct what solar and wind were doing in a way that you can't do with other
Customers' demand.
generators that choose when they run. So with some of this, you can reconstruct it. With others, there is this block of
unknown.
generation where we really don't know.
Yeah.
Now, you can imagine the leisure centre with its swimming pool. Customers would start to complain if the water was too cool. So they do have CHP plant, and you've got no real you don't really know when they're generating and heating the water. But you could say, well, if you could predict when you're going to be running your plant, if we suddenly needed some demand reduction, that could be offered as a service, because you've got a huge thermal store of hot water, which
There's some discussion of that. I think that's not that difficult. But the fact there is being too quiet. If there's not a volunteer, I might have to call on one of you. So, any questions back there?
Can I still ask a question?
Sure, you're fine with that.
Well, we had that presentation on the distribution level and the problems caused by renewable at the distribution level. I think I remember reading in some text from the transmission system operators that one of the problems that they have, and for which they are looking for solution, as a matter of fact, was how to coordinate or how to interact the management of those renewable at the transmission system and at the distribution level. So the question is very simple, because the meeting is about new mathematical problems. Would this change the techniques or the models that we have in terms of unit commitment and dispatching? So it's a very narrow question, but would that change them? And do we know how to change them if we want to integrate the problem that we have with renewable downstream at the distribution level and at the transmission level? Given that apparently we already have problems with forecasting at the unit commitment level.
Can I have it go at a first attempt? Just based on, so the first thing is that if we really did have automated demand response, say, for example, I mentioned in buildings. So if heat and ventilation was mandated to accept a local regulation signal from the grid and adjust their consumption up and down 10% to help out, then this would be local balancing signals that would take into account the transmission system. And so that could be, it might only handle some portion of that volatility, but I think that's something that could take care of a lot of the problem. And so that would be one layer, and then of course hopefully battery technology will get cheaper, and that could also take more local regulation signals. So that's my dream, and maybe someone who's has more expertise can.
But is that compatible with what you said about not knowing how to have decentralized control?
Oh no. So you see, I mentioned that I have this local regulation signal. Now it is true, and thank you. If given the number of the way this has been diced up, I have a feeling you might need it. My dream is actually probably 3 layers of 3 signals that each house would have, for example. There could be a local frequency measurement. There could be a regional, there's the grid level. There's a transmission, very local balancing signal, and there could also be a more global signal as well. Because there are information structures that is an open question right now.
And is that an interesting mathematical problem? Is it solved?
It's a favorite, my favorite.
Okay.
But somebody else chime in? Or?
There's also, from what you were saying, it seems the way you see it, most of your problems are investment problems. Well, so you don't foresee, you would try to be more, let's say, active and clever in the way you operate your distribution grid.
Yeah.
But it's obviously going to happen. Maybe it's not traditionally something you think of, but so what do you see? And it's also families of problems. Is it more investment or more operational things?
Well, I think it is. I think it is a bit of both, because our regulator encourages us to operate efficiently. So each 5 years we have this, what we call a distribution price control review, where we submit our plans as to what investment we're going to do, what maintenance we're going to do, how many repairs we're going to be doing, and the regulator says, right, over the next 5-year period, this is your allowance. If you can beat your allowance, you can keep the difference. If you spend more, that comes out of your pocket. So there is a big incentive to try and do things more clever than what you initially plan to do. So, for example, if you can defer the investment in a new transformer, and even if you defer it for a year or two, it's not just the money in the bank, but it's being able to spend that money somewhere else. And one of the biggest risks is that we don't know where the demand is going to grow most. Suddenly you could have a new housing estate, and that could be bringing increasing the demand of a town by 10%, and that can mean that you have to build a new significant amount of infrastructure. But if you can say, well, we've got enough capacity, but if we've got perhaps ways of managing the demand, you may be able to avoid having to build that new substation for a couple of years. And I think this is this big challenge is that, one, we've got to respond to demand and new connections, but at the same time we've got to ensure that we carry on maintaining and replacing the assets. And as you saw, we've got 170,000 kilometres of underground cable and overhead line. You're not going to be able to, even if you try to replace that over a 40-year period, that's going to be billions of pounds. The challenge is to try and do that in an optimised way, because there are going to be some cables that are going to last another 50 years, but there are going to be other cables that are going to need to be replaced next year or the year after. And it's trying to understand, well, when is the right time to replace that asset? And I think there are not a number of variables which affect when a cable is going to need to be replaced. One of which is when the man is digging a hole and he damages the cable, but doesn't report it, so nothing gets done, and then water gets in, and it causes the insulation to fail, and then you're having to replace more cable than had you been able to repair it at when it was done. So we end up having to repair. We carry out whenever the power goes off, and you're off for say more than a few hours. It means that we're having to do a repair at that time before the supply can be restored. When the supply gets restored within 3 minutes, all we've done is reconfigured the network and got you back on. And in some areas, because we're running almost an interconnected network, yes, there may be the lights may be a little bit dim, but you haven't really gone off supply. So there are degrees of how quickly we can restore customers.
Can I say something? It strikes me that you have two problems. At the moment, you don't have enough data. And in a few years' time, you're going to have too much data. And with all these smart meters.
Yes.
So there needs to be somewhere bridging that gap. At the moment, there are lots of statisticians in this audience, if I can call them that, who could probably help you with both problems. Because, even in this institute, a few years ago, there was a program concerned precisely on the question of how you manage large quantities of data, which occur in many fields, not just obviously in one. And so there's a lot of understanding of that, I think, now in this community. And in terms of the first problem, which is to find, if you could equivalent, the image I have in mind is of a doctor with a stethoscope, applying it at various points of the body and therefore giving a good diagnosis and deciding when you need to replace something in your body. So, indeed, there must be some statistical work to be put to use there as well.
Yeah. I think the challenge is to understand whether the data that we're going to get from the smart meters is going to give us the information that we really need to feed into our investment models to allow us to understand what gets replaced first. So I think that that's going to be one of the bigger challenges.
There's a comment way back here. So just
Just a remark for EDF, problem asked by Mr. Smith about the global optimization and the local optimization is a very hard problem, a tricky problem, but for me it's one of the most important, because I think in the world I don't see a lot of issues, solution to speak about the pilot by the demand, but it's currently for me it's only a dream, because the part of demand response is very few, difficult to put in place, because there is technical problems, there is a lot of uncertainty about the behavior of the consumer. But for example, EDF has to manage the electricity, optimize the global system, essentially to be able to sell nuclear electricity, because it's difficult to regulate the nuclear power plant, and it sell electricity to the distribution network. At the same time, the network distribution network has a lot of problems, because the wind farmer is injection a very lot of the resource. There is problem. There is not only problem of frequency, as Mr. Bialek said. There is problem of injection of RFP power on the network. There is sometimes intensity they go through the transformer substation. There is a lot of problem, and it's very difficult to manage the situation. I think we have to take in account in a global optimization model of exogenous variables. They are local, they are located on the network of distribution, and it's very difficult because there is we have taken account a lot of the exogenous variables. It translates in terms of constraints in the optimization global model. And I think for currently in France, the part of wind farmer is very low, but I think there is the solution are very difficult to put in place. More, there is the problem of the competition. There is a lot of competitors, and the competitor sales interruption. Perhaps do you have heard of Voltalis in France?
Oh, yes.
They sell, it's really, and if we are here, it's in particular to be able to understand that the international community do about this problem, because and I am not sure, I understand very bad English, but I am not sure to have understood some solution during this week. I think there is a lot of things to build in these terms.
Could we try to list interesting problems as a matter of fact?
Actually, maybe somebody else, just because I'm a bit tired, maybe somebody else could be volunteer to be Johnny. I'll pick on you. But just since I said it's my favorite problem, so I think it's important just to underline this, that definitely the control community, there's not a single person in the control community who can give you a reference and give you lots of counterexamples of why distributed control is hard. But if they try to give you a solution to decentralized control, they're going to take some asymptotic limits. They're going to give you a mean field game, or they're going to, you're going to take a PDE representation of an infinite number of generators and consumers and a PD approximation of their behavior. And all those things will give some insight. And then there's no way any of us would go and say, plug it in and make it work. So there's going to be insight from some of these naive models. And then there's going to be some evolution, but that's like that with everything. I mean, even aerospace, they take really naive models of airplanes, and it's taken a lot of time to get confidence and see it actually works. So I think I'm just saying in terms of like the controls area, it's one of the most important problems. The most difficult problem I still think is policy, is incentivizing resources. But then the hardest control problem is understanding the decentralized control. Absolutely.
But would you say that you can solve that problem through decentralized control?
No, well, I think I do know the elements, because I mean, mimicking what happens today. I mean, what do we do today? See, the thing is that we have a working system today, and why does it work? It's basically really conservative. There's really low gain, feedback everywhere, because there's an understanding of the uncertainty in the system, and And it's even working today, like, for example, the Pacific Northwest, where you have the regulation signal now goes above a gigawatt and below a gigawatt. I mean, you can get a gigawatt ramp in 1 hour, and the regulation signal looks that bad. The fairly naive, fairly distributed control techniques are working. I can't prove why, but they are. And so based on that success and all, I think to a certain point, like the things we've talked about, for example, HVAC looking at local regulation signals, it would work to some penetration of renewables. I have some confidence. If I try to extrapolate beyond 50%, say, I don't know. And I'm sure that would need, and I believe we'll always need some roughly centralized information. I believe we'll always need an air traffic control. That's my gut feeling. So, this is just all intuition from.
Our transmission system operator, and we don't have that much solar, has problems with decentralized solar. I know.
Well, there's problems today, but some places they're working fairly well, depending on what resources are available. And so the biggest problem in the Pacific Northwest in the U.S. is they don't have the resources. It's not that they don't have the control solution. There just aren't the resources to ramp up and ramp down. If they had them, they could do it. If in Seattle every commercial building could ramp up and down, just 10%, it would actually knock out that regulation signal. And there are transmission constraints we'd have to talk about. So it couldn't just be Seattle. You'd have to have you'd have to have Portland involved as well, and so forth. And that's up to a certain level of penetration. But 50% almost work in the Pacific Northwest today. And with some more resources for ramping, I think you could go maybe a bit further. So it's, Johannes, you said that Ireland's this beautiful test bed. So Washington State and Oregon are the lab rats of the U.S. right now, and showed exactly what's wrong. You can see the biggest problem is lack of resources, ramping resources. That's the block right now. And not control. They're not, they're not running around for control consultants. They're running around for consultants to help them come up with policy to get these resources in place.
We're going to have just in response to Xavier's comment, but not actually having solved all the problems this week. We're sort of aware that we weren't going to. And we are planning to have an extended problem scoping session on Friday morning, when we really want to identify what it is that's particularly worth putting our future efforts into. And so I would suggest, being 5 o'clock now, that we postpone that discussion till then. And the other thing is that people can think over dinner or whatever.
The hooky.
What's what?
The Chinese is off the hook. He doesn't have to write the
They
list.
could do their homework. It's okay, but
Can I ask just a last question, because were mentioning tests and lab rats and stuff. I've heard from Mark O'Malley that Thailand is trying to, push so that it becomes really a test system if people are willing to try some new things. Is there some similar initiative in the US, and who would be ready to play? Because you say you have ideas, but would you be ready to go play?
So Duke Energy wants to play with us. So but Bonneville is so desperate right now, and there's a problem of the players. So the Northwest Power Pool and the Pacific Northwest have their own agenda, and so it's very hard to get policy through. They want to make money. They want to be the players. So if you came in and said that there are no pools in Washington State, but there's plenty of heating, and if you try to get policy in place to incentivize the installation of the things that I mentioned, then the Northwest Power Pool would just go straight to Washington. So the biggest difficulty is this, and FERC is on the side of the generators typically.
It's a test
and we're being recorded.
It's not showing the problems, not in terms of trying the solutions.
No, I'm just talking about trying to get some test bed experiments going in that area. The problem is just trying to beat past the generation companies who would try to fight it. But there are, in other places, like for example, Georgia Power in the U.S., I mean, they're very much like, they see the incentives, they get the same set of payments, for experimentation. So they're very progressive. They don't have, it's not as much fun though, because they don't have as much installed solar.
We also get the penalties if we get things
Yeah,
wrong.
and they do too.
Customers go off supply.
Yeah.
There are, we would suffer penalties, and we would get customer minutes lost is a very strong incentive. So when we are doing demonstrations, we also try and ensure that there is some form of safety net, that if it does go all horribly wrong, you can disconnect it quickly and put the network back the way it used to be.
Right. But that's not as scary to me. It's just it's the fear of competition from the other side.
Yes.
It's really because I don't know what the cost of that balancing. I don't even want to talk, but that one plus or minus a gigawatt in the Pacific Northwest. Somebody's making a lot of money providing that, and if it were true, it could all be done through HVAC. It'd suddenly be free. There'd be a sunk cost of installing the equipment, and for a lot of generation companies don't.
The challenge, the question is who pays for the installation.
Yeah, absolutely. But so that's why it's that we've said tragedy of the commons a few times. There's no way it's going to work unless there's some sort of public policy. There's just no way.
The benign dictator.
Yeah. I mean, but we do it all the time. We have all sorts of ways to regulate behavior so we don't crash things. We don't wash our laundry in the street, and we have speed limits. But I guess that's a good suggestion that we close now and continue the discussion.
I think give people time to think, and we're all getting a bit tired.
Yes.
We should thank this afternoon's speakers very much, especially those who've come along. Especially, we should thank Sean for doing so much work all day at such short notice, keeping everything going.
Thank you very much.